So let's go ahead and get started here. We want to talk about linear and angular speed. And this is speed, so it's a rate, right? It's going to be either some angle measure, if it's angular speed per time period, or it's going to be a linear speed, which would be like what you typically think of as speed, like miles per hour, meters per second, inches per minute, whatever we're looking at there. Okay, so the first, though, is our angular speed, which might be a new concept for us. And the angular speed, as it says there on your note sheet, would be the number of radians in angle changes divided by the time elapsed. So the number of radians in angle changes divided by the time elapsed. And the way that the symbol that we use for this is an omega, which looks a lot, it's a lowercase omega. It looks a lot like a W. It's actually an omega. Just a fun fact. So, and we think of that as theta over t. As we mentioned before with arc length and sector area, if you just see a theta sitting by itself, chances are it's going to need to be in radians. Okay, so for our angular speed, it's going to be the change in the angle, change in the angle or the central angle divided by the time elapsed. So it's going to be, the unit here will be radians per minute, radians per second, radians per day, whatever you want to have there. And that's going to be our angular speed. And what you'll notice is nowhere in here does it ever talk about the radius of the circle, right? It's independent of the radius of the circle. It's just how much the central angle changes. So, well, let's look at what linear speed is. This is what you might be more familiar with. But we're talking about linear speed for circular motion. Okay, so I always, it's the distance traveled divided by time. So if we're traveling in a circular motion, by time elapsed. But if we're traveling in a circular path, we know that the path is that arc length, correct? Which we called S, which is r theta. So if we let S equal r theta, or r times theta, which we have here, then we'll get that the linear speed v is equal to r times omega divided by time, right? So it's just the arc length, S, which is r times omega divided by the time. I said omega. I should have said theta, right? R times theta divided by the time. Now, this is a fine one to use. I don't really tend to use that one because if you notice, theta divided by time is just omega, correct? So it's really nice to note that if you already know the angular speed, which you're usually going to have to find anyways in the problem, it's easier to say the linear speed is just r times omega. So if you know the angular speed, you just have to multiply by the radius, and that actually gives you the linear speed. So that's not on your worksheet there. I would make sure to add that on there. And again, we're just taking advantage of the fact that theta divided by t is omega. Questions so far with that? So these are the two formulas we're using. So I think we got a total of 4 formulas we're looking at here. Arc length, sector area, all that good stuff. All right, so let's go ahead and look at our first example here. Okay, so for the first example, if you rotate a yo-yo on a 3-foot string at a rate of 15 revolutions every 10 seconds, what are the angular and linear speeds of the yo-yo? So remember, angular speed is just that change in angle, right? It doesn't matter. Now you can imagine the path. If I have a 10-foot string, the yo-yo travels a lot farther, correct? In terms of distance traveled compared to a 3-foot string. But the central angle changing, if you're just doing 15 revolutions every 10 seconds, is not changing. Okay, so you can think about if you're on a carousel or something, right? who's going faster, the person that sits out by the edge or the person that sits in by the center? Yeah, that's the extreme carousel riders get out on the edge, right? And they get the ones that go up and down. So it's like you're moving in all these planes of motion. But yeah, so it would make sense there, right? So, so with this one, the first thing we want to find, I always, even if I'm just going to find linear speed, I want to find my angular speed first because I'd love to use this equation V equals R omega. It's a lot easier to use. So in terms of the central angle, you're going to see something like hopefully radians per time period, but more likely degrees per time period, or in this case, revolutions per time period. Okay, so we have 15 revolutions every 10 seconds. So omega, we start with 15 revolutions per 10 seconds. Now, we need it to be in radians per second, so we're back to more dimensional analysis, our old friend, right? So with this, we know that there are 2 pi radians in 1 revolution. So our revolutions cancel. What's that? 30 pi over 10 radians per second, which would give us 3 pi radians per second. So that would be our omega value. That would be our angular speed. Okay, so that tells us every second it goes 1.5 rotations, correct? That's 3 pi. 2 pi is a full rotation. Okay, so that's going to be our angular speed. Now, we could use that to find our linear speed. Okay. So again, you could go back and say R theta times t, but I think it's a lot nicer here to use this V equals R times omega. So let's see, R is 3 feet times 3 pi radians per second. Now here we take advantage of the fact that radians is not it's a dimensionless unit, correct? It's really just a placeholder to tell us what we're doing, right? We're changing the central angle. So it's going to drop out, and our new unit's going to be feet per second, which is how you would expect to describe linear motion, right? A distance per time. So the exact answer here would be 9 pi feet per second. I think it would be appropriate there to approximate it as well, so it just makes more sense to us. And type that in, we get 28.27 feet per second. Would be our, right, that's our linear speed. Now if you notice, if we make the string longer, the angular speed would not change at all, correct? Right, if you make the string 4 feet long, well, this would be 12 pi. Right, it would travel a further distance per second than if you had a shorter string. Or if you make the string shorter, it travels a shorter distance. So this is, I guess, mathematics. If you're like a lifeguard, you can think about this. You twirl your whistle. Okay, so for our second example here, we still have our formulas up here. Remember, omega is theta divided by time, and linear speed is R times omega, is my personal preference, or R times theta divided by t. So a winch with a radius of 2 feet is being used to lift up a windmill blade. So I have a not very great picture, but here's the winch. It's spinning, it's pulling the cable up, right, and then the blade is lifted up. If the winch makes 8 revolutions every 15 seconds, what is the speed of the windmill blade? So here, this speed is a linear speed because the blade's not spinning, it's just hanging off the end of a cable, right? But again, I'm still going to go ahead and find omega, and then I'm going to do that V equals R omega, because I think it's just easier to think of that way. Here, if I think about it, so when I go to find omega, which would be the angular speed, it's going to be either revolutions or radians or degrees or spins or whatever per time period. So in this case, we're told the winch makes 8 revolutions every 15 seconds. Okay, so with this, omega is 8 revolutions per 15 seconds. we need to get it into radians. So we know there's 2 pi radians per revolution. Right, so those will cancel. Here, what's that? 16 pi over 15 radians per second. Usually your angular speed is always just going to be some exact value. It's just going to be some number of radians per second. Right, so that's a little more than half a revolution every second. So then we want to find the speed of the blade, which will be v. Again, I'm going to just do r times omega. And that's going to give us it's 2 feet. So 2 feet times 16 pi over 15 radians per second. Well, that gives us 32 pi over 15 feet per second, which would be the exact answer, but probably a good time here to give an approximate answer because that seems kind of weird. That doesn't make much sense, right? So as we look at this, that's approximately 6.7 feet per second. That's moving pretty good. Excellent. Questions on that? Or does everybody understand the difference between angular speed, linear speed? Right, so angular speed is just how much that central angle is spinning, how much is changing per time period. We want that in radians per second. And then linear speed is going to be your more traditional feet per second. But it's describing a circular path here, right? That's why we're using it for this. So let's go ahead and try this third example here for the potter's wheel. A potter's wheel with a radius of 10 inches spins at 200 RPMs. Again, RPMs means revolutions per minute. Find the angular and linear speed of the edge of the wheel. Now, do note the angular speed of the wheel, it doesn't matter if you're on the edge or 1 inch from the edge or from the center. That's always going to be constant, right? But the speed of the wheel is going to be different. It's going to be faster the further you get away from the center of the wheel. Okay, so take a second and try that one. Okay, for our third example here. Again, we have this potter's wheel, radius of 10 inches, spins at 200 RPMs. Now, that's RPMs is revolutions per minute, just like RPMs on your car. It's talking about your crankshaft, how fast it's spinning. So for omega, we have 200 revolutions per minute. And we need to put that into radians. So 2 pi radians per revolution. So that gives us 400 pi radians per minute. So let's have it. 400 pi radians per minute is equivalent to 200 revolutions per minute. Now, remember the reason that we're doing this is that our formula for V either has theta in it, just a naked theta, so we know it has to be in radians, or it has omega in it, which is made up of a naked theta, right? Not in a trig function. So it's going to have to be in radians. I mean, obviously, to me, like 300 revolutions per minute is a lot easier for me to picture than 400 pi radians per minute. Like I have to convert it back into revolutions to figure out what's going on. So, but then we want to find the linear speed. So I'm going to do R, which is 10 inches, times 400 pi radians per minute. Now here, the radians will go away because it's not really a unit that we have. And this is going to give us 4,000 pi inches per minute. Now, I'm going to type that into my calculator, but that's a giant number, right? That's way too big. That doesn't really make any sense. I think if you work it out, well, I didn't. I got rid of it. What do you think would be a better unit? Do you want to maybe do inches per second? Might be reasonable. Or you could do feet per minute, or, I mean, you could do miles per hour if you wanted to. I don't want to do that really. So let's go ahead and take this and multiply it by, what did I decide to do here? Oh, actually this was radians per minute. So here, let's go ahead and do 1 minute is 60 seconds. And then we're just going to get an approximation here. And that is 209.44 inches per second would be how far a point on the edge of that wheel traveled. Is that making sense to us? There? You know, so now you can answer all these exciting questions, like if you had a fly on the end of a fan ceiling flame blade, how far it would travel, like if you needed to. Yes?
So do you need to convert it into a whole number, or you can just keep it as a fraction?
What, a decimal?
Yeah, correct.
Oh, that's good. Yeah, 1 or 2 decimal places is probably fine.
I'm asking, you keep it like already as 4,000 pi over.
If you said 4,000 pi inches per minute, it's not wrong. The kind of the difficulty is like, what in the world does that mean? Like that's just sort of, it seems sort of nonsensical, basically. Even this number here, which is, what is it, 209.44 inches per second, I might make that feet per second, would I think be a lot more easy to understand. So if I just took that and divided by 12, so that would give us 17.5 feet per second. That's probably even a better measurement, right? So it's nice, you know, you have some choices here. You know, if it didn't tell you and you went ahead and said 4,000 pi inches per minute, that's fine. You answered the question. Probably if you're going to use it, or if you want to try to have it make sense to you, right, you probably want to convert something, because this we can imagine, right? We know what 17.5 feet looks like, roughly, and we know how long a second is, so we can picture that. And 209 inches, we probably convert it in feet in our head, you know? So you always want to try to get something that just seems more realistic and makes sense to you, but either way you want to do that.